Hi, welcome to my second talk at NCNGT 2021. I'm assuming you're coming from the first talk, so I'm going to talk about some applications stemming from my project with John Etnayer about classifying the symplectic fillings of lens spaces. And so there's two main topics I'll discuss. The first one is what we call the Legendrian Berge conjecture, and the second one is about Stein Cobordisms between lens spaces. So in certain places, we will be using notation that we defined in the first talk. And of course, this is all joint work with John Etnayer. So let's move on. So the first problem we'll talk about, or the first set of applications, is to the lens space realization problem and the Berge conjecture. So these are famous problems in smooth topology. The Berge conjecture concerns the question which knots in S3 admit integral surgeries to lens spaces, and sort of turning the question around, one can ask the lens space realization problem, which asks which lens spaces can be obtained from S3 by integral surgery on a knot. So Josh Green solved the second problem completely in 2013, and he was able to show that all the lens spaces that come from Berge knots are exactly all the lens spaces that you can get by integral surgery on a knot in S3. So the Berge conjecture still remains open. Our approach is to restrict the Berge conjecture and the lens space realization question to the contact topology world and change the question around a little bit. So that looks like the following questions. The contact Berge conjecture asks which Legendrian knots in the standard tight S3 admit a Legendrian surgery to a lens space. And the contact lens space realization problem asks which lens spaces can be obtained by Legendrian surgery on a Legendrian knot in the standard tight S3. Now, I'll just point out there are different versions of contact Berge conjectures that have been posed. Notably, Onaran and Geiges have asked a question, which lens spaces can you get by doing Legendrian surgery on knots in S3, and they've included over-twisted S3s in that question as well. For our purpose, we restrict our attention to Legendrian knots in the standard tight S3. Right. So this is the conjecture we pose in our paper. We claim that the only lens spaces that can be obtained by Legendrian surgery on a Legendrian knot in S3, in the standard tight S3, are LP1s. These are surgeries on unknots, and they're represented by sort of pictures like this. And the next set of lens spaces are LMN plus 1 M squared. These are lens spaces that can be obtained by surgeries on negative torus knots. And so these were both known that they are obtained by Legendrian surgeries on knots, and I believe we find this new class of lens spaces that can be found by Legendrian surgery on knots, and these are surgeries on certain Berge knots that I have given here. And for these two, the first two, you can get both universally tight and virtually over-twisted lens spaces by doing a Legendrian surgery. But for the third class, we show that you can only get the universally tight ones. So what I'll do is I'll give some evidence. I'll first show why these are ones you can get by doing surgeries on Legendrian knots, and I'll then provide some evidence as to why we believe that these are the only ones you can get. So we're studying knots, the Legendrian knots in the standard tight S3, because we want to use filling results to talk about this Berge conjecture kind of result. So the first observation is that if a contact lens space is obtained by Legendrian surgery on a Legendrian knot in the tight S3, then it admits a Stein filling with B2 equals 1, which is quite clear because you have B4 the standard symplectic B4 with S3 bounds, and all you're doing is you're attaching a 2 handle along the Legendrian knot, and that will give you a filling with B2 equals 1 for that length space. The second observation is that, so recall in the first talk we mentioned that all fillings of universally tight length spaces were described by Liska with these subscripts that are null sequences that are continued fractions that represent 0, and we've showed that those are the smooth manifolds that fill all length spaces. You can get some different symplectic structure that fill the virtually over twisted ones. And so a simple observation just from the picture that gives these manifolds is that if W with the null sequence N1 through Nk fills a length space whose P over P minus Q expansion is given by M1 through Mk, then the B2 of the filling is just given by the difference between the Mi's and the Ni's, and you subtract 1 from that. So combining these two, we get an idea of which length spaces have Stein fillings with B2 equals 1, and we can conclude that if LPQ admits a B2 equals 1 filling, then the P over P minus Q expansion, M1 up to Mk, has to be of the following form. There will be a null sequence such that all the Mi's agree with the Ni's excepting 1, and that one is 2 more than the corresponding entry in the null sequence, or all the entries in the Mi's agree with the null sequence entries bar 2 of them, and for those two they disagree by 1. So that's all that can happen. So based on these two observations, we found the following families of length spaces. And so LP1, it's quite clear that they're Legendrian surgeries on a single knot because they're represented by just the unknot. But we can also see that the P over P minus 1 expansion looks like 2, 2, 2 up to 2, and a null sequence that works is just the null sequence 1 and then 2's and then 1, and you can see that there's a difference of 1 for these two and everything else agrees. For the ones that come from surgeries on torus knots, some of the work was done by Liska in his paper when he classified all the length spaces that have rational homology ball fillings with B2 equal 0. And following from a similar arguments there, we were able to show that if a null sequence has only one index equals 1, then the null sequence where the first one is increased, then the rational number given by the continued fraction expansion where the first entry is increased by 1 and the 1 is increased to 2 looks like mn plus 1 over mn plus 1 minus m squared. So the length space it corresponds to is L mn plus 1 m squared. And then for the third family of length spaces, it turns out that the continued fractions expansion for these look like 2's and then 1, 3 and then a 2 and an n, and there's a null sequence that fits it, which is all 2's, then a 1 and an n, and you can see that these two differ by 1. So this null sequence gives a B2 equals 1 filling for this length space. Now, it's not true that a B2 equal 1 filling immediately means that you have surgery on a knot, right? And so what we were able to do is, once we drew the pictures, we were actually able to reduce them through some Legendrian Kirby calculus to actual pictures of knots to a surgery picture with just one knot. But why we believe that it doesn't work for any of the other B2 equal 1 fillings is that in most cases the Kirby diagram for a filling with B2 equals 1 is given by a version of the following, where you have one the one handle representing the S1 cross D3 to which the links knots get attached, and then you have two torus knots on the boundary S1 cross S2, and they link in this following manner. You need the filling to be simply connected, so that will mean that these two numbers have to be co-prime. But even if they are co-prime, unless it's these two cases, one of these two cases, we were not able to work out the Kirby calculus that reduces the above pictures to one with a single two handle. And as far as we are aware, that we're not aware of any techniques that will actually allow us to prove one or the other, but it brings an interesting question that can one prove or find moves that work, either that this cannot be reduced to a picture with a single two handle, or actually do that, or reduce it to a single two handle, in which case we'll have more lens spaces that are realized by Legendrian surgery on a single knot in S3 standard. Right. So moving on to the second set of applications, we explored Stein Cobordisms between lens spaces. So the first result we proved to sort of nudge us along in this direction was that we were able to classify the maximal B2 of a Stein filling of a lens space. And we prove that the maximal B2 of a Stein filling is given by the number of components in the Legendrian chain diagram that gives the lens space. And the maximal filling is unique up to diffeomorphism and given by attaching two handles to B4 along the linear chain that gives the lens space. And the idea to prove that was just that the filling corresponding to the null sequence 1, 2, 2, 2, 2, 1 is the filling that comes from the plumbing, and it has the maximal B2. So given that led us to the following theorem, which says that if there exists a Stein cobordism from one tight lens space to another, then the length of the continued fraction expansion of P over Q, so the one that's at the bottom, so you have LPQ here, and the cobordism gives you LP prime Q prime at the top, then the continued fractions expansion for the one at the bottom cannot be more than the one on top. And the idea is just that if you had the Stein cobordism, you could then attach the filling here, and the B2 of these would be additive since they're both Stein. And we were also able to prove that if in fact you have equality in the lengths of the continued fraction expansions, then actually both the lens spaces, both the contact lens spaces have to agree, in the sense it's the same tight contact structure and the same lens space naturally. And also the cobordism is an H cobordism. Now it's a question that one can ask: is the cobordism as an H cobordism, is it actually smoothly trivial in that, is it just a product? So that's something we were not able to answer, but we think is interesting to explore. So the second set of applications to Stein cobordisms, which we find really interesting, is that we were able to construct examples of lens spaces L1, L2, L3, such that there's a cobordism from a virtually over twisted structure to a universally tight structure on L2 to a virtually over twisted structure on L3. Now, the fact that you have cobordisms from universally tight to virtually over twisted is quite obvious, because you can just consider the lens space given by these three. This is universally tight, and you can attach a two handle along this particular knot living in the boundary, or living in this lens space. Attach a two handle along this knot, and that will give you a lens space which is virtually over twisted, because you have a knot here which is stabilized on either side. But this is what was really interesting about these constructions, that we found cobordisms from virtually over twisted lens spaces to universally tight lens spaces. And so there's broadly two ways were able to construct them. And the first one was by reducible surgery on Legendrian large cables. These were kind of interesting examples of knots living on convex tori in contact manifolds that were the examples were first found by Yatsui. They were further studied by McCullough. And this is an example of the cobordism you can get. The pink curve here is a large cable. It actually sits on the mixed torus in this lens space. And its TB is one more than comes from the torus framing. So you can do a torus frame surgery, which is a reducible surgery. And then you can attach a two handle here to get something that's universally tight. Now, the geometry of large cables has been completely understood by Chakraborty, Etnayer, and Min, and they have the following classification result that if you have a knot on a convex torus T in a contact manifold and the maximal TB of K is exactly torus framing plus 1, then T is exactly a mixed torus in that there's two basic slices that are of opposite signs and T is in the middle of them. And what Legendrian surgery on this knot does is it sort of removes these two basic slices and leaves you with something that has like less virtual over twistedness coming from that particular T2 cross I. So the second class of cobordisms we find were sort of sporadic surgery diagrams. These were first pointed out to us by Mark Kegel. And for these, so this is an example of it. This here is not a cable this doesn't lie on the torus, but it's a cable of a torus knot. And if you do surgery on this by some Legendrian Kirby calculus, you can do this following reducible surgery, and then you can get from here to this universally tight lens space. So a question we think is interesting is, what is the geometry of this? So in the previous case, Chakraborty, Etnayer, and Min, they understand for knots living on tori, they understand exactly when the max TB is going to be more than the torus framing. I mentioned just torus framing plus 1, but they classify exactly when you can get to torus framing plus n. But for these knots, it can also be an interesting project to try and figure out why the geometry works out like it does and why Legendrian surgery on this knot removes the sort of virtual over twistedness coming from the mixed torus. So this is the question: is can one understand the geometry in these situations? So thank you for your attention. I'll stop here. Please do let me know if anyone has any questions. I'll be holding office hours on the 21st at 11. Yes.